Hi, and thanks for joining this Telit Cinterion webinar, Maximizing Battery Efficiency in Cellular and LPWAN IoT Deployments. I am Amanda Flink, the head of global events here at Telit Cinterion, and I will be moderating today's event. Quickly to get to know our speaker, to explain this topic today, I am pleased to be joined by Tymek Lipinski, a hardware engineer at Telit Cinterion. Now, just before I hand it over to Tymek to start our presentation, I do have a few quick reminders. I'd like to remind our audience that we will have time to answer some questions at the end of our presentation. You may simply submit a question by posting in the questions box that is located near the bottom of your screen. Also, please be sure to check out the resources section for some additional information on our topic today. There you can find today's slide deck and links to a few other things that might be helpful to you. And finally, we will send out the replay link to all attendees at the conclusion of this webinar, so be on the lookout for that. And with that, Tymek, I will hand it over to you to start our presentation today.
Thank you, Amanda. It will be a pleasure to share with all of you some quirks and things about battery efficiency in Cellular and LPWAN. I'm working as an application engineer in Telit Cinterion, supporting daily customers. Let's kick off. Some agenda about the presentation that we will cover today. How we introduce new project and how we prepare our requirements. What are our power saving options? Some power saving usage. How much energy is required to do X, something, upload, download some data. How to optimize our energy usage in our application, and hardware solutions for low power devices. We start off with requirement gathering. Firstly, we establish our software requirements. We have to define our frequency of communication, what kind of protocol we will be using, our responsiveness of our device. Do we need to wake on demand from external signal? How big will be the payload? How many updates we need to provide and service? And most importantly, how to sleep and save energy. Once we are ready with our software requirements and general idea about our project, we have to establish some hardware requirements. What will be the expected lifetime of the device? Factor in the battery life. What is our cost constraint? How much money we can spend on the hardware? Is it going to be a low-cost device or a high-cost device? What kind of environment the device will be deployed in? So mainly temperature, humidity, vibration. What are our options for host wake-up? We have to wake up our host, of course, to do something periodically. And most importantly, what is our space and size constraint for our hardware? Once we are ready with software and hardware and general project idea, we have to validate our requirements. Does it make sense and can we support? So does hardware support the software power hunger? Can we withstand the increased current consumption for certain scenarios? It might turn out that we need to modify our software requirement to match the reality or modify hardware requirement to match the software requirement. When it goes from requirement into design, we usually start off with choosing a provider and subscription management if needed. We can select from few options like VPN or public IP. Do we need local or world coverage? Will our device be mobile? What kind of data plan we expect per year? How many megabytes? Do we need a normal SIM or eSIM? Do we need subscription management? Once we are done with that, we go to our select components, so the hardware part. What kind of brains we will be using? A simple MCU, more beefy MCU, SoC, system or chip. Maybe we'll be using module embedded services. What kind of module we will be selecting? Which category, which radio access technology, and what features do we expect from the module? What kind of battery we will be using? Non-rechargeable, rechargeable, high capacity, low current? We have to decide. Then we select power components, which will provide power and juice for our electronics. Then expected protection components, ESD, surge, EMI interferences, that all have to be covered. And last but not least, sensors and interfaces because our device has to do something except from connecting to the internet. Once we have that filled in, we need to find out our dev boards and utilize them to validate the design. So Telit, Cinterion, and other vendors, especially for the power components, battery modules, and so on, provide development boards, which ease up development stage and trial, because then we can measure desired scenario and measure and know what will be the expected power expenditure during the device operation. We also have to test and measure failure scenarios. So there is no network, poor coverage, server is down, modem could not register to network, rejected us for whatever reason. That also has to be covered and taken into account. Dev board, right, variety of selection and options to choose from to tailor down to your design. When we are ready with our design and dev boards and so on, we integrate and provide test samples. And we do excruciating tests regarding temperature, functional, power consumption, design optimization, stress testing, and pre-certification. We want to score the pre-certification because when we launch the product, we just do start of production and we just do a one final costly but a single time certification, and we are ready to launch the product into the market. Let's talk about some software requirements. This is a very broad topic because it covers how to sleep, how to use the module, how to use the network provided features, and what to expect in terms of current consumption, and how they intertwine and influence each other. First, let's focus on the frequency and data uplink and downlink. So, when we approach our project, we have to determine how often the device must send and receive data and how much data will be sent and received. Daily, hourly, monthly, yearly. We need to factor in updates, of course, of our system and of the module if necessary. We have to determine if the device must be woken up by the server message. So if we want to poll the device externally, will there be any special events that must trigger data upload alert in terms of alerting like vibration, temperature, or other physical external event around the device? And we always have to consider worst case scenario. This is where usually our systems fail because we haven't figured out the worst case scenario for our device. Then we have to again confront requirements and reality, and of course what is possible to achieve and develop. We need to think, do we really need to pull the device remotely? And how can modem achieve maximum power saving so that we have the best quality out of our battery? Protocol selection. Well, we have a wide variety of options to choose from. We have point-to-point protocol, other words PPP. We have W1 and module services. Both PPP and W1, they provide simple host driver. They don't need extensive AT command driver to service the module AT commands and function, but they have limited sleep options and they have slight power consumption or overhead. On the other hand, module services, which are integrated into module AT interface, they provide best power efficiency. They have variety of services available. Unfortunately, they require extended AT driver on the host site. Which protocol will we use for the data itself? Will it be TCP sockets, UDP, MQTT, any other? Well, depends on what we are trying to achieve with our application. If we need data confirmation about delivery and acknowledgement, then TCP is the one to go. It has a very slight energy overhead because if the packet is not acknowledged by the server or vice versa, the packet will be re-uploaded to the network. It's really suitable for bulk and small data transfers using unsosulated result code or transparent mode on the module, depending how much data you're sending. It's really flexible because on top of TCP sockets, you can implement your own external protocol for whatever you need. UDP, best energy efficiency. In short term, just throw a packet and forget about it. There is no confirmation of connection or delivery, just like with our streaming services like Netflix. It's suitable for bulk and small data transfers, so URC or transparent mode-based communication with the module. And we have MQTT. It's really easy to use solution, very popular, highly integrated with cloud services, and it's best fit for small data packs and broadcasting them to many endpoints. Unfortunately, MQTT has its drawback with protocol overhead and some extra energy consumption and keep alive settings. Then later we decide on our SIM subscription, what kind of SIM we will be using. So we can use normal public SIM, maybe VPN, or public static IP SIM card. Well, the normal public SIM card, it's cheap, it has simplified network infrastructure, but it has some possible security concerns and it requires extended server logic. VPN, on the other hand, simplifies server logic. It has very improved security because it's a virtual private network. Nobody else, external actor, cannot get into this network. But operators require extra payment for VPN option, so it's costly. And unfortunately, as in VPN, usually means that a certain SIM card has a static assigned IP, it incentivizes using modem as a server, which is not the greatest idea, which we will explain later. Last, public static IP. Well, it's nice because it's reachable from anywhere, from our phones, from our laptops, anywhere you're connected to the internet, you can reach that one particular module, but it opposes a serious security concerns, and there's no control over external traffic. That means that any external bad actor could reach to our device and do some harm. Not to mention that internet is full of bots that are called crawlers. They probe all of the available IP ports and IP addresses. So the side effect might be that some bot is constantly keeping our module active and consuming energy. Let's jump into a quick glossary of modem-related radio states and how they translate into power consumption. The most popular term and most common one is idle. In general, modem is attached to the network and it periodically listens, so to say, to radio according to eDRX intervals. While in idle, there is no active data exchange between modem and the network, but the modem is registered and ready to send or receive data. eDRX, it's an abbreviation for discontinuous reception. This is something wonderful that 3GPP invented to save power. It means that modem only listens to the network signal in time intervals, and we call it a paging. It can happen in the intervals of 0.64 seconds, 1.28 seconds, 2.56 seconds, and so on. And it highly depends on current network operator settings, and it varies from location to country to continent. Then we have eDRX, so it's an extended DRX. This was introduced later on in LTE evolution to further increase energy saving. The thing is that it provides a longer time period during which the modem switches off the radio completely up to 46 minutes. When the eDRX cycle ends, the modem goes back into idle and it listens to paging according to the DRX timing. Later on, we have the RRC, Radio Resource Control. I will use this term a lot because when RRC is active, It means that the modem is actively sending and receiving data, even though we are not sending any IP traffic. This means that the modem is actively consuming power, outputting RF and decoding the RF from the base station. Next, we have the paging time window, PTW. This is time during which modem uses the DRX time to listen for paging, and PTW is in the eDRX cycle. PSM, Power Save Mode. Wonderful development from 3GPP specification, where modem switches off the radio completely up to 3 months, and the network retains the registration and the notion of presence of the modem in the network. Ultimately, we have Suspend. This one is pretty quirky because it's a Telit specific abbreviation. On top of the PSM, where the radio is switched off, modem nearly completely switches off and only runs the RTC, meaning real-time clock, to keep up the time and to know when to wake up when the power save mode timer expires. Responsiveness of the system. We have idle. In idle, we have large current consumption. It means that the modem is always available for external signal, but it consumes roughly 8 milliamps in CAT-M with DRX64 and 2 milliamps with DRX 2.56 seconds in NB-IoT. That has a significant impact on responsiveness of the system. So always available, but consuming power because we are actively listening. Then we have medium consumption of eDRX. That means that the modem will be available every X minutes for Y seconds. So every X minutes, during the X minutes, modem is consuming 0.5 milliamp, but it's consuming then 12 milliamp during paging time window, during which the network can probe the modem and wake it up to establish data connection. Then we have extra evolution of the system, very small consumption, so it's eDRX joined with PSM and Suspend. So the modem will be available every X hours days for Y seconds. So during X hours or days, the consumption goes down to 4 microamps or even lower. And when we are waiting for signal, it's 0.5 milliamps. And when we are actively listening for the signal, it's 12 milliamps for a very short period during paging time window. PSM and Suspend. So this is the best solution. It's super small consumption, very similar to previous one, but we skip the 0.5 milliamp waiting period, and it's simply below 4 microamps while we are sleeping, and roughly 1000 microwatt hour for each wake up and data transfer and download. What are my options to wake on demand? Of course, from the server. Idle, in short, very quick, but power hungry. eDRX and Suspend, slightly slower, but greatly reduced consumption. eDRX, PSM, and Suspend, the Telit Cinterion specific, becomes unreliable due to PSM timer. So when we want to go into PSM, the modem, our application, requests the network, okay, I want to go to sleep for 24 hours. And the network may respond with, okay, you have been granted 24 hours of sleep, or the network may reply, no, I grant you 18 hours of sleep. So this shows a problem with synchronization between the module, the device, and your server, because you are not able to inform the server about the PSM timer assigned from the network. You just go to sleep. And it also applies without the eDRX, just the PSM and Suspend option. It becomes unreliable due to PSM timer. What's the main difference between eDRX and PSM? Well, first off, the timing. eDRX is just longer no listen. PSM is longer complete sleep. But the key difference is at the end of each eDRX cycle, there is no need for active reporting. So modem does not tell the network, hey, I'm back. No, modem is just simply sitting there and listening if there is any information from the network for me. In case of PSM, after each cycle, so after each wake up of the modem, it has to perform something called TAU. This is tracking area update. So the modem has to reach out to the network, establish RRC data connection, and then perform tracking area update operation. This is by definition from the 3GPP standard, and modem has to do that. And this is a consumption overhead. So in some cases, we have to calculate, is it more suitable for our application to rely on eDRX or maybe PSM? Some of the prerequisites for entering PSM suspend mode. First off, we have to ensure that our SIM is not pin protected unless the modem and SIM support SIM suspend feature. Then we have to jump to UART, so our serial interface. Power saving has to be enabled. Then we check another interface available on some of our modules, USB. We have to ensure that it's either disconnected or suspended. And last but not least, there are no active data connections. So no socket listeners, no PPP, no TCP, UDP active in the background because they will lock out our modules from entering the full power saving feature. How do we wake up our host? So let's assume our modem finished the PSM time and it wakes up. So what does it do to wake up the host? So most commonly used is the ring 0 indicator of the serial interface. If that's not available or we have another solution, we use V180 or PowerMon assertion. So that's a pin available on the module OGA footprint that goes high when the module leaves the off state or deep sleep state. In some of our products, we can configure a dedicated GPIO that will toggle when the module wakes up. And for some simplified application where the MCU or SoC is capable, we can have URC on UART. URC stands for Unsuscillated Result Code. So when the modem switches back on, it simply sends a short message on the serial interface to the host, and this can be used as a wake-up trigger for the whole system. Let's discuss our options to wake host on demand from server. So in my opinion, it's not really suitable for low power devices. And why is it not suitable? Well, listening and having some features active is always burdened with energy expense for both radio and logic. Why? Because radio has to listen for the paging, right? And listening for radio means that all of the DSPs and radio processing units in the module have to be active, even for a short period of time. That's energy consumption. And also logic has to be ready and prepared, memory allocated for receiving the signal and doing something with that, because we ultimately receive an IP packet. So in the end, if it's a must, application has to be really properly tailored towards wake host on demand from external server. Let's go into some visual representation of the terms we discussed today. Key remark here, the precondition for this current capture was that modem was previously attached to the network and physical location of the modem did not change. So here modem was in deep sleep, averaging 0.6 milliamp during this period. We can see a small blip. Most likely, modem had to do something within its flash memory, so it had to increase the current consumption momentarily. Modem was deregistered from the network. So here we have UART active, averaging 10.5 milliamps. I forced the modem to wake up its UART interface by sending few 80 commands just to show the step change of current consumption. So when the UART interface is active, modem will draw current. Then we issue a command to modem, search for network. So the modem starts searching for a network and proceeds with network attachment. This process took 2.5 seconds. We had pretty good signal conditions, so the average current was 70 milliamps. It was pretty short, and because the modem was previously attached to the network, it knew which frequency to scan first, because the modem always remembers last known base station frequency, radio access technology, and operator. Later on, after we are done with the registration, we no longer exchange data with the network, but we had to establish RRC here to communicate, to register with network. And this RRC is kept active by the network for 5 seconds. This was specific for this particular CATM operator. So the average consumption was 60 milliamps, and it took 5 seconds because that's the timeout for this operator. When it's finished, the network releases the RRC connection, it becomes inactive, and modem goes straight into eDRX cycle, consuming roughly 0.6 milliamps. When the eDRX cycle finishes, we go into paging time window, during which we have the DRX intervals of listening to paging. So the modem goes, is there anything for me? Is there anything for me? Is there anything for me? And it goes on for 10 seconds. 10 seconds was my requested configuration. We have a variety of timings available. We can make it shorter, we can make it even longer. After the paging time window and probing the paging signal, the modem decides, okay, there was nothing for me, let's go back into low power mode, eDRX. Let's discuss how much energy we will be consuming. First off, in CATM. So in CATM, the best energy efficient solution is the PSM, so power safe mode. In this mode, modem simply switches off and consumes below 4 microamps of current. Modem wakes up every PSM cycle and is ready for data upload. Typical wake-up energy expenditure, 550 microwatt hours. Let's discuss and put this value into some perspective later on, because it's really important how much energy we should expect from the modem to require to perform certain action in the network and in the system. UDP upload and download, 1 kilobyte each way, 970 microwatt hours. This is not on top of the 550. 550 is just, we were sleeping, we wake up, ready for data upload, nothing to do, go back to sleep. UDP upload and download scenario of 1 kilobyte each way, 970 microwatt hours, that was, we were sleeping, we wake up, we send, we receive, we go back to sleep. And that's again for CATM network. And that's with the specific network operator who uses 5-second keep alive RRC. Of course, when the modem goes into power saving mode, we can mash a button and modem can be hardware woken up at any given time and proceed with data. Let's compare it to NB-IoT. So, best energy efficient solution, again, PSM feature for NB-IoT. Again, modem simply switches off and consumes below 4 microamp hours just for running the RTC to know when to wake up. Typical wake-up energy expenditure, 850 microwatt hours. Okay, so what's going on here? NB-IoT was supposed to be more energy efficient, right? Well, that heavily depends on the network operator configuration of those parameters like DRX and RRC active time. UDP upload and download of 1 kilobyte, now it's 1000 microwatt hours, so 1 milliwatt hour. That's a lot. But that's with a very nasty operator, which keeps the RRC for 10 seconds. So even though we are already done with any kind of data upload, we still burn energy for 10 seconds because that's how this operator configured his base station. Let's use different operator for the same example, which keeps the RRC only active for 1 second after last data transfer. Look, it dropped to 509 just to wake up and go back to sleep, and upload and download jumped down to 726 microwatt hours. That's really nice. It could be even lower because we were using a very long active time for the PSM timer. It was 30 seconds, but we were using a different operator. Let's look at current consumption curves. So this is the first example. So it's CAT-M, PSM suspend mode. Here, the modem was completely sleeping for below 4 microamps of current consumption. Then modem either wakes up on its own, or we trigger by mashing the on button. Modem loads the system, activates and configures the system, starts searching for network, finds the network, sends 1 kilobyte, receives 1 kilobyte, and then we have this unfortunate 5 seconds of doing nothing because we have the RRC keep alive. When we have not sent any data or exchanged any information with the network releases the RRC connection here, so the current consumption plummets. Then we just listen to paging, 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 paging. All the way here, we prepare for PSM suspend because there was no data traffic, no activity. Last one blip, and we go to sleep, and we are back to below 4 microamps of current consumption. So in order to wake up, send and receive 1 kilobyte of UDP data in this particular scenario, it took 25 seconds and it consumed nearly 1 milliwatt hour of energy. Let's compare it to the NB-IoT with the nasty operator A, which has the RRC for 10 seconds. So again, below 4 microamps of current, the modem wakes up, loads the system, initializes the system, searches for a network, attaches, sends 1 kilobyte, receives 1 kilobyte, and then it does nothing for 10 seconds, just burning our precious battery energy, doing absolutely nothing, just sustaining the radio for whatever reason, because the operator requires that. After 10 seconds of no data activity, the network releases the RRC connection, modem goes into active time, does paging, paging, anything for me, hello. Then we have preparation for suspend, last blip, and then we are down to below 4 microamps of current consumption. Is there a way out of this? Yes, 3GPP was considerate enough to include something called Release Assistance Indicator. In short, RAI. So this is the nasty operator A with 10 seconds of RRC keep alive. How does it look? We were sleeping, 4 microamps of current. We load the system, activate, configure the system, search for a network, send some data, receive some data, send the release assistant indicator to the network, and network says, okay, no data in, no data out, let's kill the RRC. It releases the RRC, modem goes back into paging, 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 anything for me, preparing for the suspend mode, and it goes to sleep below 4 microamps of current. Look at the energy, 680 microwatt hours compared to previously over 1 milliwatt hour. This is how much energy saving the release assistance indicator gave us with this particular operator. Please memorize this value, 680, because this is the nasty operator with release assistance indicator. And this is the operator B, the one with 1 second RRC keep alive. This time we are not using the release assistance indicator, and the active time was very long. So let's go through this scenario again. 4 microamps of current, system initialization, loading, searching, sending, receiving, 1 second of RRC keep alive, and we end up with releasing the RRC. Here I must have sent an AT command and woken up the modem interface, And then we go paging, paging, anything for me, hello, what's going on? Okay, nothing for me, let's prepare for suspend and go to sleep. And this cycle took 43 seconds and used 76 microwatt hours. So 1 second RRC of operator B versus release assistance indicator. So 680 versus 76. But please note that the active time here was very, very long. If we make it shorter via the requested PSM timer configuration, we could easily go below 500 microwatt hours per such cycle. So how much energy we are consuming and how can we lower it? The best solution is the network supported release assistance indicator. This can help us to beat down the, let's say, so-called silly values of 5+ seconds of RRC keep alive setting on the network side. The release assistance indicator cuts down simply on unused RRC energy to absolute minimum. So when we are done sending and we are not expecting any data to come back to us, we just use the release assistance indicator, tell the network we are done, and the network goes, yeah, okay, you're free. So simply put, send the packet away and disable the radio. The realistic energy expenditure can be brought down to around 500 microwatt hour per upload wake up. That also varies between selected modem variants. Then we have expenditure of the sleep, so the 4 microamps of current for 24 hours of sleep of around 290 microwatt hours. So if we add them up, that means that we are consuming for 1 communication cycle per day roughly 800 microwatt hours. So how long our device will work consuming this much energy? So a year, it would be nearly 300 milliwatt hours. So let's select first one available battery that is cheap from the market, lithium non-rechargeable battery, 1.2 amp hours at 3.6 volts. That's roughly 4,000 milliwatt hours of available energy. Please note this is overly simplified. This is just an example. In reality, we have less energy available. That would mean that we could run the modem to communicate every single day for 15 years. That's kind of crazy. But somebody is always stealing our juice, our energy. So the first stealer is the DC to DC switching converter efficiency. If it's not working at very set conditions, the efficiency goes down and we are burning energy into heat. We are losing it and wasting it. Then we have losses, leakage. So capacitors do not only leak fluid, they also leak charge. They discharge and they have leakage current. We have variable network conditions. So the network coverage may be pretty bad, or somebody took our device into basement and the modem is struggling to communicate with the network. We are out of coverage, so the modem keeps scanning the network and consuming power to decode every single available channel because it's struggling and wants to attach to a network. We have to factor in our host energy consumption. Have we achieved maximum current saving and power saving on our host device? We have to factor in the self-discharge of our battery because every single battery will self-discharge. That's why they have a shelf life. We have to factor in temperature derating. So every component will behave differently in a set temperature. So especially capacitors and diodes, their characteristics will change and their leakage current will change with the temperature. Same goes on for age derating. For every single component, we have to factor that in because age has a big role to play in designing the devices to be launched with a single battery for 5 years into the field. So let's summarize. Who is stealing our jewels? First, the eDRX value. So how often does the modem listen for the paging from network? Then another one is the RRC activity timeout. because if the network configures 5 seconds and does not support the release assistance indicator, we will be in a pickle, a lot of wasted energy for nothing. Ultimately, to validate everything, we have to request our mobile operator for test SIM cards, and we validate and check the design in real network to see how it behaves. We introduce attenuation, we introduce noise to simulate worst case scenarios. We also have to be pretty wary about something called PDN release disconnect behavior of the network. When the network notices that we have an active LTE connection, that means this is the PDN connection, IP connectivity, but there is no data transfer for extended time, like 2 to 8 hours, the network may decide to disconnect or release the PDN connectivity. For the modem, it means that it was simply deregistered from the network. The network said to the modem, go away. What will modem do in this case? It will reset its connection, search the network again, and attach. And network will allow it because it's a new activation of the PDN. So it only happens when there is no data traffic from or to the modem. Sending any kind of data will reset this timer, so it gives us another chance. And this is usually happening for, let's say, normal consumer SIM cards, so the typical internet SIM cards available in shops. We can beat around this problem using dedicated M2M, so machine-to-machine subscription of our operators, but we have to check with them. Please, every time, remember to check with the mobile operator if for any reason they have enabled or disabled the PDN disconnect when there is no data traffic, even on M2M SIM cards. What happens when network releases or disconnects the PDN? Well, connection loss will break our UDP or TCP return port. So we need to do a reconnect because essentially we have lost the pipe between modem and our server in the mobile network operator infrastructure. Other caveats. Well, what happens when we have CATM or NB-IoT, we are using eDRX or Suspend mode or PSM or Suspend mode, and right in this moment, our server sends some data packet, 1 kilobyte to our modem. Well, there is a buffering option on the base station itself. So the network acknowledges those packets, and the network knows that the modem is currently in eDRX or in PSM mode. So network is unable to deliver this packet right now. So network will buffer it until the modem becomes available. But mobile network operators never guarantee the packet delivery. MNOs rarely specify buffer size or timeout of this packet. So how long the packet will be held in the base station and how big of a packet we can send and be sure that it will be buffered. It's worth contacting the mobile operator. What is their settings? Maybe they will promise us something. So general advice from us would be, please avoid relying on the buffering. And please remember that all of the inactive connections are really disliked by modems, servers, and networks. So if we open a TCP connection and we do not send any TCP keep alive packets and we have some default configuration, it is really likely that the connection will get reset, broken, and we wouldn't be able to communicate with our server. And if this happens, the modem will be upset because it will try to send the packet will not reach the server, so modem will try again, and it will burn through precious battery energy stored in our device. We have to also remember to have some spare joules, So we have to factor in the update of our host, so our brains, MCU, SoC, whatever we are using, and we have to consider some spare joules, extra energy, extra capacity in the battery for module updates using, for instance, FOTA, so firmware over the air update. We have to estimate the energy required for a single update for both host and module. We have to assume that few updates will be required over the device lifetime, both for host, bug fixing, feature implementation, maybe adjust for new server infrastructure. But it also concerns the module. Maybe there will be critical security update, feature update, bug fixing, anything like that could happen. And we also have to always count in the worst case scenario. So we have very poor signal and it's a very big update. Let's look at a current capture of realistic case using firmware over the air update. I have specifically selected a very nasty one that is long and it's quite big. That was 240 kilobytes of incremental update downloaded from an FTP server via CATM network. The update starts with modem was in full PSM suspend mode, consuming below 4 microamps of current. Modem wakes up, finds network, communicates with UDP server, and it receives information, okay, it's time for update. Here is the server information. Modem validates the server information and starts downloading the data. Once it finishes the data, it goes into update. This part, the FOTA download, it took 32 seconds to get 240 kilobytes from the server, and it used 3.4 milliwatt hours. Whoa, that's almost 4 to 5 days of our battery lifetime just to download 240 kilobytes of data. But then modem goes into special bootloader mode and starts working on its flash memory, moving segments and performing the update according to the 240 kilobyte of the incremental update instructions downloaded from the server. This process took 210 seconds and consumed 11.5 milliwatt hours until the moment the modem rebooted and registered back to the network. So that's nearly a month out of our battery lifetime that we expect the device will have, a single update. So we really have to factor that in. Please remember that each time update time and size will be different for each individual product, release, revision update, or anything like that. This is why we encourage you to always approach us to provide you with some figures and graphs like the one we saw before about the energy consumption required for the FOTA update, right? Let's jump into hardware part. So some hardware considerations of the design. Battery selection, very important topic. And we have a wide variety of batteries on the market. And they have different qualities and specifications. So first of all, output voltage. Do we want lower or higher output voltage out of our battery or a battery pack? We have different peak current that the battery can provide. We have self-discharge characteristics which are different for each battery chemistry and manufacturer and temperature and load current and so on. We have different sizes, in turn, the energy density of those batteries, and we have different temperature operational range of batteries. What we are left with, in the end, we can select a big battery with low current. So low current output means that the battery itself is not able to deliver sufficient current for modem peak current consumption for radio operation. So that's where we should consider a supercap, so supercapacitor in our circuit to cover up for the peak current consumption. And some of the Texel batteries look nice, are quite popular, pretty okay in terms of price and volume, and they have very flat discharge curve. So the flat discharge curve is nice because when the battery goes with time, the voltage stays pretty much flat, and only at the very end of the battery expected lifetime, the voltage starts to plummet. That's easy to detect by the application and prevent switching on to avoid brownouts on our system. Auto selection, we can go with a very big battery with high current capability. So it can be used solo. We don't need any external support circuits like DC to DC converter or supercap. One from Ultralife is very nice. It has a flat discharge curve, but the drawback is cost. It's really, really costly. Some power circuit considerations. So we go and determine the absolute max current consumption of our entire system under worst case scenario. So we factor in age, time, temperature, and network conditions. We have to validate our battery capability. So can our battery supply sufficient current? And we have to include the lowest battery voltage at the end of life of the battery when it's nearly empty. Do we need support from a supercapacitors just to cover short-term current spikes? Ultimately, we go with voltage stability. This can be maintained by a tailored down DC to DC converter. DC to DC converter shall be used in a smart way. Modern DC to DC converters provide a wide variety of modes of operation: CCM, DCM, PFM. Most interesting one is PFM, pulsed frequency mode. It allows the DC to DC converter to lower its quiescent current consumption to a very low value because it's only bumping up the output voltage when the light load is applied to it. So when the module is sleeping, it's consuming microamps, it will be very small current draw. So the DC to DC is a safe keeper of safe voltage level, and it just goes blip, waits, blip, charges up, blip, charges up. During all power modes of the modem, sleep, PSM, suspend, we can switch off the DC to DC because we can run the modem straight from the battery, even if the battery voltage is below normal nominal modem voltage supply. The modem is sleeping, it's just running the RTC, so the real-time clock, so we can lower the voltage, in some cases for some products down to 2.6 volts. We can also utilize a split power supply of the modem. Some of the modems come with separate supply for brains, that's the baseband, BB, and separate supply for the RF, so that's the radio part. That gives us some flexibility in terms of building more efficient DC to DC or power delivery circuits for the modem because we can utilize different voltages for both BB and RF. Here is a simplified example of a block diagram of the power delivery circuit. So we have our battery cell that is not capable of supplying sufficient current to the modem. So we utilize a DC to DC converter block in here, which is controlled by the modem power indicator. Modem power indicator could be derived from the Vaux power mon pin or from V180, depends on the design. So when the modem power is on, it immediately enables the DC to DC to have full nominal voltage supplied to the modem. And we utilize some kind of power switch max or ideal diode to avoid backfeeding here and there. And we power our modem. When the modem goes into super low power mode, we disable the DC to DC, and then modem is powered straight from the battery. It goes through our max switch or ideal diode to the modem, and modem is happy. And we are not essentially wasting current to run the DC to DC converter for a very long period of time. So it's hours or maybe days in some cases, right? Another example is how to utilize a supercap. So we have battery cell with very, very low output current, but it's cheap. And we like cheap components, right? We use a very small DC to DC converter that is current limited. And we control it using either modem power indicator or our microcontroller charge up. So general GPIO will be sufficient here. We decide, okay, let's prepare for data upload. We enable the DC to DC. We store our higher voltage in our supercapacitor, which can be 5, 10, 20 farads, depends on the application. And then we have optional MOSFET switch so that we can isolate the modem from the supercap when the modem is, for instance, fully powered off, because we don't want any parasitic drain from the supercap when we don't need it. Finally, we enable the switch and use the supercap to cover the current requirement of the modem for the data communication. Why are we even using the DC to DC? Why are we even using DC to DC? Well, of course, we want to squeeze as much as possible out of the battery we paid for, so every single microwatt hour is precious, right? Shall we use supercap or even maybe bigger DC to DC? Well, the thing is that supercap makes for cheaper DC to DC because we don't need to cover up so much current requirement from the module. And it generally allows to use cheaper batteries. It also enables us with energy harvesting. We can have a small solar panel and use the energy of sun to power our device. How we can further cut down on microamp draw? Who is again stealing our joules? Usually pull up and pull down resistors in our circuits. They will chuck few microamps here and there. So we usually select as high as possible value on them, down from 100 kilo ohms up to mega ohm range. But we have to be cautious with this selection because we need to maintain signal integrity, voltage levels across selected temperature range of the device to operate. When we are selecting transistors to switch something, to translate voltage levels, to control something, we favor MOSFETs over BJTs because BJT, when we trigger the BJT, it has to consume some current, few microamps to run. MOSFET, we just use the current for a split second to charge up the gate and it stays on this way for as long as we don't change the state to another one. We have to validate leakage current of selected capacitors. So every single capacitor will have some kind of leakage current and self-discharge. We have to factor that in. That's a big consumer that is really silent and sometimes really difficult to notice. And we have to pinpoint sweet spot for our DC to DC operation. We want to achieve as high efficiency as possible because we are not happy with wasting energy into heat. So all in all, we can provide you with support on hardware, connectivity, software, and custom solutions. We are really ready to support. We have a vast department of application engineering engineers that are on call with you to help bring up your device. If you have an idea or you need to validate it, maybe do a reality check, you are unsure, please reach out to us. Are you unsure about the solution? Are you thinking the right way? Maybe you want to check with the experts? We are here for you. Do you want to explore some possibilities? Check the latest network trends, technology, applications? We're on it. Are you limited by your equipment or staff? We can test it for you. We can provide the pre-certification. Thank you very much for sharing your time with me on this very interesting topic, and I hand over the microphone to Amanda. Thank you very much.
Great presentation there. I hope our audience got what they needed from that. Real quick, before we get to the questions, audience, I am going to drop a poll on your screen. If you'd like to have one of our experts contact you directly, maybe you have a really specific question to your application, please just respond here on the poll and we will get you connected with someone. We do have time for just a few questions. There's still time to ask a question as well, so feel free to submit in the box on your screen there. Time, we've gotten just a couple, so let me just pick a few and we will go through these in the time that we've got left.
Sure.
The first question I have here, what are the key trade-offs between using NB-IoT versus LTE-M in terms of power consumption and also coverage reliability?
So the key trade-off here between CATM and NB-IoT is the mobility issue. So CATM is designed to support moving between cells between base stations. So it's still suitable for tracking, let's say, vehicles, bikes, people, dogs, cats, and so on. On the other hand, NB-IoT was designed to support only stationary devices. The device can recover if it's moved from one location to another and it forces modem to use different base station, but this will have some current consumption overhead because network is not aware of it. So it will break connection and we have to establish everything from scratch. Of course, NB-IoT is slower, and key benefit from using CATM is that usually we want to download more than we want to upload. CATM works the other way around. It has higher bandwidth on the uplink than the downlink. So we really need to validate what we need for our application.
Yeah, great. Next question we have gotten here: what hardware level strategies are most effective for deep sleep modes in ultra low power?
So mainly I have seen a very big success of designs where they incorporate a very cheap battery, which is passively powering all the low power modes of the circuit. And then when the time comes for communication, for triggering data traffic, for uploading, downloading, updating, they use a DC to DC converter, which is small, which charges up a supercapacitor of a better quality supercapacitor that has a very low self-discharge characteristic. And this is how they achieve low-cost device with pretty much no wasted energy for sustaining the operation. And the best thing I have observed so far and had experience with was using NB-IoT with suspend mode, PSM suspend mode enabled in such hardware situation, and using the release assistance indicator with the network and using UDP transfers. So throw a packet, expect or don't expect an answer, throw the release assistance indicator, and go back to sleep. Basically, the devices I have met are meant for metering and working 5 to 8 to 10 years in the field without any service requirement. So no human action or serviceman visit to replace the battery. And they factor in at least one update of the modem, full flash memory, and the device, the host MCU, which is around 256 kilobytes of memory, plus 1 megabyte of external flash memory.
Great. We'll take just one more question as we are coming up on the hour here. And I really like this one. What about security features like TLS or DTLS? How do they contribute to energy consumption?
In general, when we are sending something over the radio, we have the RRC, which is consuming something between 60 to 400 milliamps of current, depending on the modem radio output power. So when we factor in TLS, DTLS, encryption, it's done on the fly on the modem. Maybe there will be a bit of protocol overhead, but once we have the RRC established, the added current consumption of this extra encryption engines is hidden by the RF consumption. So it does not make a spottable or a visible difference in the current consumption curve and total energy usage. So in other words, it's more energy efficient if we cut down 1 second of our RRC than not to use security features like TLS encryption, certificate validation, client certificate validation on the server side if we want to be really, really secure in those terms. So I would say use TLS wherever you can, because that's how you protect your data, your system, your infrastructure, and your company.
Yep, and we all know how important security is.
Of course, yeah.
I think that is a great place for us to wrap today. Audience, again, check your inboxes in the coming days for that replay link. spend some time in the resources section here. There's a few different articles and things that you can take a look at. Taimek, thank you so much for your time today. Really, really appreciate it. And thank you everybody who joined us.
Thank you very much. I wish you all a lovely day and see you next time.
Thanks.